In this video, we're going to continue with our lecture on vector-valued functions. So we're going to talk about the derivative of some vector function r of t here. And that derivative is just the derivative of each of the real valued functions in each coordinate. So r prime of t is just the vector function x prime of t, comma, y prime of t, comma, z prime of t. Moreover, this derivative vector is called the tangent vector to the curve C defined by r of t. Why do we call it the tangent vector? Well, just like with a real valued function, if we take the derivative, if we have a two-dimensional curve here and we take the derivative, what do we find? Well, we find a tangent line, which can be described by a tangent vector in 2 dimensions, or at least the direction of it can be. And similarly, we have the same thing going on in 3 dimensions, where if we have an r of t, so some position vector in 3 dimensions, then we can find a tangent vector in 3 dimensions, and we just do that by taking the derivative of each component. All right. Moreover, if we have a position function r of t, which is x of t, comma, y of t, comma, z of t, if that is a position vector of a particle moving along a curve in space, then the velocity is the derivative of r of t. The speed is just the magnitude of that velocity vector, and the acceleration is the second derivative of your position vector, or in other words, the derivative of the velocity vector. Let's go ahead and do an example here then of a type of problem like that. So let's find the velocity, speed, and acceleration of a particle whose motion in space is given by this position vector at the point where t is equal to pi. All right. So if we do that, let's see, we have r prime of t, which is our v of t. So let's take the derivative. The derivative of 2 cosine is negative 2 sine. The derivative of 2 sine is 2 cosine. And the derivative of t squared is 2t. So that is our derivative vector, or our tangent vector. We want to know what that is, though, at t equals pi. So you plug in t equals pi. So v of pi is equal to negative 2 times sine of pi. Sine of pi is 0. Negative 2 times 0 is 0. Cosine of pi is negative 1. So 2 times negative 1 is negative 2. And then we get 2 pi. And that is it for the first part of that question. So that is our velocity vector. Then we want to take that velocity vector and find its magnitude. That will give us the speed. So the speed is equal to the magnitude of that vector. So we get 0, the square root of 0 squared plus negative 2 squared plus 2 pi squared, and all of that is equal to the square root of 4 plus 4 pi squared, which is here. And then we want to take the derivative, the second derivative of our velocity function, of our position function, second derivative of the position function, so the derivative of the velocity function. Well, if we recall, v of t was equal to negative 2 sine of t, 2 cosine of t, and 2t. So the acceleration vector is derivative of negative 2 sine is negative 2 cosine. Derivative of 2 cosine is negative 2 sine. And derivative of 2t is 2. Then we plug in t equal to pi, so the acceleration vector evaluated at pi, and we get, let's see, cosine of pi is -1, so -2 times -1 is +2. Sine of pi is 0, so we get 0 there, and then we get 2. And that is our acceleration at t equal to pi, our acceleration vector at t equal to pi. All right. We're going to move on and do a couple more examples. So we got the tangent line to the curve C defined by r of t at p is defined by the line, defined to be the line through the point P parallel to the tangent vector. So you may want to recall first that we write out the parametric equations for a line as x is equal to x naught plus at, y is equal to y naught plus bt, and z is equal to z naught plus ct, where x naught, y naught, z naught is a point in our line, and the vector abc is a vector that is parallel to your line. So it's the direction vector of your line. So what does that mean? That means we want to find the direction of this tangent vector v of t, and then we want to know a point, which we are given, and then we can come up with our parametric equations for the line. So the first thing you want to do is you want to take the derivative of this vector here. So we have t squared plus 3 to the 1/2 in the first coordinate. We take the derivative of that, and that would be 1/2 t squared plus 3 to the -1/2 all times 2t. Do our chain rule for the derivative there. All right, and then we have the derivative of ln of t cubed plus 3. And the derivative of that is 1 over t cubed plus 3 times 3t squared. And the derivative of t is 1 for the third coordinate. And we want to evaluate those at some certain point t. What point would that be, though? Well, we have a position vector here. And we want to evaluate what the direction of the tangent vector is at some t that is helped to be defined by this point here. So what t value creates this point right here? Well, notice that the z coordinate is t and z is 1 here. That really implies that t is 1. Let's verify. If we plug in t equals 1 for r of 1, then what do we get? We get 1 squared is 1 plus 3 is 4, and the square root of that is 2. Then we plug in 1 into the second coordinate. We get 1 cubed plus 3 is 4, so the natural log of 4. And then we just plug in 1 and we get into the z coordinate and we get 1, which is exactly the point here. So in fact, t equals 1 is what we were looking for. So what does that mean? That means we want to plug in t equals 1 into this. So v of 1. Let's see, we have 4 here in the denominator. This is 1 over 2 times 4 to the 1/2 power. It's supposed to be 4 to the 1/2, so let's just write that as square root of 4. Times 2, almost left that off, times 2t. So times 2. And then we have 1 here, so this is 1 over 4 times 3 times 1 squared comma 1. So our velocity vector, our tangent vector, our tangent vector here is, let's see, it's 1 over 4 times 2, that's 1/2, comma 3/4, comma 1. Okay, and this is our A, B, and C. So write that down right now, 1/2, 3/4, 1. And we put all that together into our equation, our parametric equations. We get x is equal to 2 plus 1/2 t. Y is equal to ln of 4 plus 3/4 t. And z is equal to 1 plus t. And that is our parametric equations, which we have written down here as well. Okay. Got 2 more examples here. Now, I want to find a vector function r of t such that v of t is equal to e raised to the t, comma 1 over 1 plus t, comma 1 over the square root of 1 minus t squared. And r naught is 1 comma negative 2 comma 1. Okay. What does that mean? Well, first off, if v of t is this formula, is this vector valued function, we want to find r of t. Well, you do that by integrating, right? We remember that for the derivative, we just took the derivative of each component. To integrate, we just take the integral of each component. So here, r of t is going to be equal to e to the t plus c. Let's call this C1 because it's going to be some constant here that's different than the constants we get elsewhere. And then the integral of 1 over 1 plus t is natural log of 1 plus t plus some C2, some other constant. And then the integral of 1 over the square root of 1 minus t squared. You'll have to think back to some work in Cal 2, but that is arc sine of t plus some C3, some other third constant. Okay, well, r of 0 is 1 comma negative 2 comma 1, so let's go component-wise. So x of 0 is 1. Where am I getting that? X is your first coordinate, and that evaluates to be 1 there. So x of 0 is 1, and this is e to the t plus c, where t is 0. So this is 1 plus c. So we get 1 is equal to 1 plus c. In other words, c is equal to 0 here. All right, same thing. Y of 0 is equal to negative 2. Moving over here, plug in 0. 1 plus 0 plus C2. Okay, ln, the natural log of 1 is 0. So this tells us that C2 is negative 2. Perhaps I should have written that as C2 here, which implies C sub 2 is negative 2. And then z of 0 is equal to 1. Again, where are we getting that? That's up here. And then we take our equation for z, which is arc sine of t plus c3. Except we want to plug in 0 there. So arc sine of 0 plus C3. Well, arc sine of 0, what does that mean? That means what is the angle that we have to plug in to output a 0 when we plug it into sine? Well, that angle is 0. So we in fact get 0 plus C3 here. This implies that C3 is equal to 1. All right, and then our final answer is this vector up here. That's what we're looking for, except we can plug in C1 is 0, C2 is -2, and C3 is 1. So our final solution is e to the t plus 0. So we can just leave that as e to the t. ln of 1 plus t plus a -2. And then arc sine of t plus 1. And that's it for that problem. And then finally, for our last problem in this section, find r of t if v of t is equal to 2ti plus etj plus t e to the t squared k. Well, again, we want to integrate. What is the integral of t of 2t? That is t squared. What is the integral of e to the t? That is, oh, I messed up. T squared plus what, everyone? That should be plus some constant c. All right, then the second component is e to the t plus some constant c. Again, these constants are different. And then what is the integral of t e to the t squared? dt, make our u substitution. U is equal to t squared. Du is equal to 2t dt. So this is 1/2 the integral of u du, which is 1/2 times 1/2 u squared, which is, wait a second. Oh, no, sorry guys, sorry everyone. I miswrote something here, and I was so confused why I was coming out like that. Okay. U is t squared, but this was e to the u du. That was our function up here. Sorry. There we go. T e to the t squared becomes 1/2 e to the u du. After that change in variables, u is equal to t squared. And then we take the integral of this, and we get 1/2 e to the u. And from there, this is 1/2 e to the t squared plus some constant c. And this was plus c. All right. So we get, again, 1/2 e to the t squared plus some constant c. Now, what we have seen here is that r of 1 is equal to this vector. So when we plug in 1, we should get 2. So if I plug in 1 here, we get 2. So 1 squared is 1 plus, what does C1 have to be? That implies that C1 has to be 1. All right, if we plug in 1 into the second component, we should get 1. So if, let's do that, let's write that here. We get 1 is equal to e to the first plus c2, which tells us that c2 is equal to 1 minus e. Okay, C2 is equal to 1 minus E. And then if we plug in 1 into this last equation here, we should get out E over 2. So into this equation. Or this expression here. So the equation is 1/2 e to the 1 squared plus c sub 3 is equal to e over 2. Well, that implies that C3 is 0. Okay. We put all of that together. And our first coordinate was t squared plus 1. Our second coordinate was e to the t plus 1 minus e. And our third coordinate was just e to the t squared over 2. Because again, we don't add anything here since our C3 ended up being 0. And that is it for this video.